Hi, everyone. I hope that you've been doing well, that you moved out okay. I wanted to check in and give a little video lecture about Lesson 10, Regression Assumptions. So this is the natural building point for all of those models that you guys did in the group lab. And in fact, you're going to be asked to use the tests described in this lesson in the last lab. So what are regression assumptions? Regression assumptions are certain assumptions that we have about our data. And if those assumptions are true, then regression models will work very well. They will predict our outcomes very well, and it will be a good model. If your regression assumptions are false, then you are assuming things about your data that are not true, and your model isn't going to be an accurate representation of what's going on. So we need to keep these in mind. There are 5 assumptions of regression of a linear model, also sometimes called an ordinary least squares regression model. So there are 5 assumptions, and we can really boil them down to 3. So the first one, as you'll see on the workshop or the lesson document that I have up here, the first one is linearity. The second one is no multicollinearity. And the third one is independence of observations. Okay. So, there's technically another one, but it's kind of small potatoes. You got to have a large enough sample size, right? So your model is limited to the sample that you have. As we learned in the previous workshop, our F statistic is deeply related to the sample size. So if you have a smaller sample, it's going to be harder to have a significant F statistic. Fun fact. Anyways, so sample size matters. Having big samples allows us to make better inferences about our data because there's more data points to explain variation in it. So it's very helpful. Okay, so once we have that data, how do we look at these 3 assumptions: linearity, no multicollinearity, and independence of observations? Well, first we can define them, and then we can test for them. We can identify, do we have it, do we not? Okay? So, what is linearity? Linearity means that your predictor has a linear relationship with your outcome variable, specifically with the mean of the outcome variable. This means that as x increases, let's try this your direction, as x increases, y also seems to increase. Okay? Now, that shape, there are lots of different shapes. For instance, if as x increases, your data goes, that's not really a linear trend, right? Regression is going to be terrible at modeling that. There are some techniques that are good at modeling that, a loop-de-loop pattern, right? But we don't cover them in this course. So if your data, as x increases, if y generally increases, right, we can show that relationship. Same thing is if you have multiple predictors and the outcome increases. Makes sense. We're trying to find a best fit line, and lines are linear, so we kind of need the data to have a general linear trend in order for it to work. Okay, so what wouldn't be a linear data set? Non-linearity in your data might be if the relationship was actually exponential. Okay, so exponential curves look like this. They're curvy. And if your relationship is exponential, A linear model will like sort of get it, but there are special models that are better for exponential relationships. Okay? Okay, so multicollinearity, what's that? Multicollinearity is the idea that your predictors aren't overly related to each other. After all, let's say that something like your income and how and the amount you are taxed. Okay, so these two things can be very different due to weird tax laws, but generally we expect that if you pay more, if you get paid more, you pay more in taxes, right? So these two things would be generally very closely correlated. If we try to use income and how much you pay in taxes to predict an outcome of like of how likely you are to vote, right? These two variables aren't going to play well together because they are almost identical. Regression doesn't really know what to do with that. Multicollinear variables, multicollinear predictors tend to make your R squared skyrocket. So when you have multicollinearity, you tend to get R squared values of like 1 or 0.998. Things that should make you think, is that right? Like, that seems too perfect. And your model estimates, your beta coefficients, they aren't reliable either when you have multicollinearity. So how do we deal with multicollinearity? First, you could transform the variable in some way so that it still reflects the general pattern, but in a slightly different format that's not collinear. Sometimes people square a vector. Sometimes they take the log of it. Sometimes they will. No, those are pretty much the two big ones. And sometimes you just have to take it out of the model. Okay, so we don't want multicollinearity. We don't want nonlinear relationships. What's the third big assumption of regression? It's called independence of observations. This means that cases are independent of each other. The opposite would be interdependence of observations. Why does this matter? Regression assumes that all of your cases, all of your rows in your data sets, your observations is what we call them, it assumes that none of their outcomes are more related between like two members than the rest of members. They're all like independent. They didn't rely on each other. Here's an example where an outcome for an individual might have to do with might be interdependent. For example, if your model, if you're looking at students, right? Students tend to be in classes together. A student's, whether they do their homework or how well they do on their homework, that might depend not just on the student. I mean, it depends on the student, but it might also depend on the class. For instance, let's say that some classes suddenly had to go online because of the coronavirus, while some classes didn't. Class is going to matter. It's going to affect the outcome. So if you don't control for class, what's going to happen? The residuals for some students will be much more similar than for other students. In other words, the model will predict that the outcomes for students in the same class will be very similar. And that's not how this model is supposed to work. You don't need to know too much more, but it does these two other things, which are the other assumptions of regression. If your cases are interdependent, your residuals stop being normally distributed. Instead of being like this, where some cases are extremely well predicted, some cases are extremely poorly predicted, and some cases are just like, in the middle, they start getting very skewed, where a lot of cases are poorly predicted, a lot of cases are very well predicted. Okay, and it means that you have non-constant variance. We want the variance in residuals to be constant. That means that we're doing like a pretty good job for all of our data points in predicting their outcomes. But if it's non-constant, if the variance in your residuals depends on certain groups, then you're not doing a good job of predicting all cases. You're predicting some cases better than others. This would mean a bad model. Okay? Great. So we have learned 5 assumptions of OLS regression, of regression models: linearity, no multicollinearity, independence of observations, normality, and constant variance, also called homoscedasticity or heteroscedasticity. Say that 5 times fast. Have fun. That was like most of Stats 2 for me, learning to pronounce that consistently. Okay, great. We can use the tools introduced in this lesson to check all of these really quick. I'm going to go over a few. First, as you see in the text that I've highlighted, ggplot can visualize relationships between outcome and explanatory variables. This will tell us, is there a linear relationship? VIF, a function in the car package, can calculate something called the variance inflation factor. VIF is really useful. It gives you a single number for each predictor in your model, and that number tells you whether there's multicollinearity. Then there's NCV test, which is a straightforward test that tells you whether you have non-constant variance. It's pretty useful. Okay? So we can actually switch over to RStudio, where I've copied the code for the rest of the class. And it is taking a moment to load. Great. So here we go. What we're doing here is we're using something, a data set from the ISLR package, which I believe everyone has access to. If you don't, just install it. And we're grabbing 1,000 credit reports. So each row in our data is a customer, and their outcome is going to be how much credit card debt they've accumulated. And we can try and predict that using their age, using their income, and using how high a limit on their credit card they have. So what do we do with this? Well, we can just straightforwardly download the data from RStudio Cloud, on RStudio Cloud, and we can check. We can select variables and give them more convenient names, like we've done here. We can also run our model, which is going to be a straightforward LM function. We can view our model and view our beta coefficients and alpha coefficients, but we can also start testing model assumptions. I'm going to follow this up in a couple minutes with another video that describes our